This is the sharpest image of the Sun ever taken. It reveals something scientists have waited for more than a century to see. Because this is not just a clearer photo. It may be the first step towards solving the oldest problem in solar physics: why the Sun's outer atmosphere is hotter than its surface. For decades, scientists have been trying to understand how energy moves from the surface of the Sun into the corona, and in this image, they may have finally seen one of the ways that happens. Today, I'm going to explain what scientists have been waiting more than 100 years to see, why it matters more than almost any solar discovery before it, and how it could change everything we thought we knew about our own star. So let's start with a question. If you asked most people what the surface of the Sun looks like, they'd probably say smooth. Maybe a giant ball of fire, something simple. But look at this image. See all those bright blobby shapes packed across the entire surface, pressed together like a giant honeycomb? Those are called granules. And each one of those shapes is a colossal bubble of superheated gas rising up from deep inside the Sun like a fountain. Each granule is roughly the size of the entire state of Texas, and at any given moment there are more than 1 million of them covering the Sun's surface all at once. Here's how they work. Hot gas from deep inside the Sun pushes upward through the center of each granule. That's why the middle looks brighter. When it hits the surface, it spreads outward, cools down, and sinks back into the Sun along the dark edges. Then it heats up again, rises again, and the whole cycle repeats over and over, every 20 minutes. This process is called convection. It's the same fundamental process that drives plate tectonics on Earth: magma rising, spreading, cooling, sinking. Except on the Sun, the gas inside these granules moves at more than 7 kilometers per second. That's fast enough to break the sound barrier. Fast enough that when it crashes into the surface, it generates actual sonic booms that send shock waves rippling across the star. The Sun's surface is never still. It is always boiling. But here's what scientists could never see before this image. Zoom in on the edge where two granules meet. In every photo of the Sun taken before this one, that edge looked like a soft, blurry line. Just two bubbles gently touching. But in this image, that edge is curling. Little swirls, little loops, like smoke peeling off a candle flame. Spinning and curling all the way around every single granule in the picture. And that is what scientists have been waiting over a century to see. These are called Kelvin-Helmholtz instabilities, and they form for a beautifully simple reason. The gas cooling and sinking on one side of that edge is moving slightly differently than the gas on the other side. And whenever two things slide past each other even slightly out of sync, the boundary between them doesn't stay flat. It buckles. It curls up into a spinning loop, a tiny whirlpool. Each one of these whirlpools is only about 50 to 65 kilometers wide, the size of a city. On a star so massive you could fit over 1 million Earths inside it. Finding these in a photo is like standing on a beach and spotting a single grain of sand. Except this telescope didn't find one, it found thousands of them, scattered across the entire image, all spinning all at once. Scientists had predicted these whirlpools existed for decades. The math said they had to be there, but no camera had ever been sharp enough to actually see them, until now. So why does this matter? Because of a mystery that has haunted solar physicists for nearly 100 years. Here's the problem. If you stand near a campfire and take a step back, it gets cooler. That's just how heat works. The farther you get from a source of heat, the less of it you feel. The sun should work exactly the same way. The surface should be the hottest part, and as you move outward into the wispy outer atmosphere called the corona, it should get cooler and cooler. But that is not what happens. The surface of the sun sits at around 5,500 degrees Celsius. Scorching, unimaginable. And yet, the corona floating above it reaches temperatures of over 1 million degrees. 1 million degrees. It's like walking away from that campfire and suddenly catching fire the farther you get. It makes no sense. And for a century, nobody could fully explain why. But look back at those tiny whirlpools. The sun's surface isn't just hot gas. It's threaded with invisible magnetic field lines running through everything, like threads woven through fabric you can't see. And every single time one of those little whirlpools spins, it grabs onto those magnetic threads and twists them, like winding a rubber band tighter and tighter around your finger. Now imagine millions of those whirlpools, all spinning at once, all across the surface, all twisting those magnetic threads, tighter and tighter. What happens when you wind a rubber band too far? It snaps. And when these magnetic threads snap, they release a burst of energy. And that energy doesn't spread outward in all directions. A huge portion of it fires straight up into the corona. So here's what scientists now believe. Every one of those tiny whirlpools you can see in this image is constantly twisting and snapping magnetic threads across the entire surface of the sun. All day, every day, sending burst after burst of energy upward into the corona. And that might finally be the reason the corona is so much hotter than the surface below it. The surface isn't just radiating heat outward passively, it is actively pumping energy upward through millions of tiny spinning whirlpools, like an engine nobody knew was running. Now, why couldn't we see this before? It comes down to the sheer difficulty of what this telescope achieved. Previous tools, like NASA's Solar Dynamics Observatory, gave us extraordinary views of the sun. By imaging it across different wavelengths of light, scientists could see solar flares, colossal loops of plasma arcing hundreds of thousands of kilometers into space, and vast coronal holes venting solar wind across the solar system. Remarkable images. But even those couldn't resolve something this small, this close to the surface. The granule edges still blurred into soft lines. The whirlpools were invisible. The Daniel K. Inouye Solar Telescope changed everything. Built on the summit of Haleakala in Hawaii, it uses a 4-meter primary mirror, the largest of any solar telescope on Earth, combined with adaptive optics technology that compensates for the distortion caused by Earth's atmosphere in real time. The result is a photo sharp enough that for the very first time you can actually count individual whirlpools. Instead of squinting at a blur where the edges should be, you can see every curl, every spin, clear as day. It's the difference between knowing something must exist and actually seeing it for the first time. So, what does this change? If scientists can confirm that these whirlpools are the mechanism, or even one of the mechanisms, driving energy into the corona, it would close a gap in our understanding of the sun that has been open for nearly a century. It would mean the answer was sitting right there on the surface the whole time, in structures we could see but never quite resolve. It also raises a bigger question. If these whirlpools exist on our sun, they almost certainly exist on other stars too, which means this isn't just a discovery about our solar system. It could be a discovery about how stars work. full stop. And this is only the beginning of what the Inouye telescope will show us. As it gathers more data, higher resolution, longer observation windows, scientists will be able to watch these whirlpools form in real time, measure how much energy they actually release, and test whether that energy is truly enough to account for the corona's impossible temperature. We might finally be closing in on the answer. The Sun has been burning for 4.5 billion years. Humans have been staring at it for all of recorded history. And it took until now, until this image, to see what was happening right there on its surface the entire time. That is what makes this photograph extraordinary. Not just the resolution, not just the technology, but the fact that the answer to one of the oldest questions in solar physics might have been hiding in plain sight, written in a million tiny spinning whirlpools, just waiting for a camera sharp enough to finally read them. Thanks for watching, and if this blew your mind even a little bit, you know what to do.